Hi everyone, and welcome to another video where we're looking today at infrared spectroscopy. Now, infrared spectroscopy is a really interesting technique, and it is based on the premise that all covalent bonds vibrate, rotate, flex, stretch, bend, etc. And each bond does that at a unique frequency. What that means is when you hit a molecule with infrared radiation, if it's at the right frequency, then that energy will be absorbed by the rotating bond, or flexing or bending or stretching. If it's not at the right frequency, then that energy will be transmitted and will go straight through to the detector. So you basically have a source on one side, a detector on the other, your molecule in the middle, you pass the light through, and away it goes. Now, what we're going to look at today is how an IR spectrum is organised or structured, and some of the key peaks that you want to be looking for in your IR spectra. We may or may not get onto matching spectra to functional groups. Okay, so like I say, the premise is that each of these bonds vibrates at a different frequency. The infrared radiation is usually over a range of different frequencies, and so all sorts of different bond types or energy for all the different types of bonds will be absorbed at different frequencies. The frequencies at which the energy is absorbed will tell us about what functional groups and what bond types are present in the molecule. Okay, so that's the general concept. Now, in this case, when we look at our spectra, what they are is a graph of energy transmittance. So at the top of the spectra is 100% line, and if there's no energy being absorbed, then 100% of the energy will be transmitted until something is being absorbed, in which case the transmittance decreases. So let me show you what that means. The molecule shown above is ethanol. Ethanol has carbon-carbon bonds, carbon-hydrogen bonds, hydrogen-oxygen bonds, and carbon-oxygen bonds. At the different frequencies, and that's what the baseline shows is the different frequencies, then energy is absorbed or transmitted as appropriate. So the top of the line shows 100% energy transmittance, and as the lines dip down, that shows the energy being absorbed. So first we have the OH stretch, then we have the carbon-hydrogen stretches, then the carbon-oxygen stretch, and the carbon-carbons hiding down in there as well. Okay, so that's the general premise behind it. What does this actually mean in practice? Well, you can kind of divide up your spectra into, I would say, probably 3 chunks. You've got the stuff on the left-hand side of the spectrum, which is between 4,000 wave numbers at the far left and 2,800 wave numbers. Now the unit is centimetres to the -1, or wave numbers, which is simply the inverse of wavelength. That's the frequency. So at that left-hand side of the spectrum, you will find bonds to hydrogen. That's oxygen-hydrogen, nitrogen-hydrogen, and carbon-hydrogen bonds. And they all stretch at around that frequency. Triple bonds, if they occur, will be at a slightly lower frequency. The other really key one is double bonds, carbon-oxygen double bonds, carbon-carbon double bonds. You'll also find carbon-nitrogen double bonds. And they tend to be pretty much smack bang in the middle of the spectrum at around about 16 to 1700 wave numbers. Okay, the third section of the spectrum is what we call the fingerprint region, and that is the stuff on the right-hand side of the spectrum. That is really diagnostic, but you pretty much have to be able to compare it with a known sample of your a known spectrum of your compound to say for sure whether that is what it is. And that tends to be where you find your single bonds. Carbon-carbon bonds, carbon-nitrogen, carbon-oxygen, carbon-chlorine, carbon-bromine, etc. We might look at a few bits and pieces in that region, but we won't look at much. Okay, so when you start off and you're looking at your spectrum, the first area you want to look for is in this, oh, yeah, 2,800 to 3,500 range. And at that point, you will see some very distinctive peaks, which can identify the presence of an alcohol or a carboxylic acid or a primary or secondary amine or amide. Okay, so what do they look like? Let's have a look. Alcohols first. Alcohols are wonderful. They're this beautiful, strong, parabolic shaped peak that you can see there highlighted in blue on the left-hand side. They're very symmetrical, they're very strong, so they get, probably nearly 90% absorbance of your energy, and they are really, really clean. If you get a peak that looks like that, you can go, aha, I have an alcohol. Now the jagged peak just to the right of that at about 3,000 wave numbers is your carbon-hydrogen peak, and you're going to see that in every single spectrum, okay, because every single organic molecule is probably going to have a carbon-hydrogen bond. Exactly how it looks is going to vary a wee bit, so there are a couple of little tricks. But in general, that carbon-hydrogen peak is not something you need to be looking at a whole lot. Okay, here's another example of an alcohol. You can see again that really clean looking parabolic peak. Now, this one is more interesting. This is a carboxylic acid. So if we just go back to the alcohol, that peak there on the left-hand side that I said is an alcohol peak is actually the oxygen to hydrogen stretch. So it's from that OH bond that's present in an alcohol. Now, you also have an OH bond present in a carboxylic acid, but the presence of the carbonyl group, the C double bond O, has the effect of really broadening that peak. And so what happens is the OH stretch from the alcohol, which is around about on the left-hand side of this sort of green shaded area, and the carbon-hydrogen peaks, which you're going to sort of end up merging together. And so you get this peak that I tend to describe as the big, fat, and ugly peak. It can take anywhere up to nearly a quarter of the width of the spectrum. It is incredibly distinctive. It's just such a big, fat, messy, ugly peak. The other thing you'll get with a carboxylic acid, as well as that fat and ugly peak around the oxygen to hydrogen and carbon to hydrogen peaks, is you've got a carbon-oxygen double bond. And so that you see as the really strong bond in the middle at around about 1700, 1720 wave numbers. And that again is quite distinctive. The third peak there, which is highlighted in blue towards the right-hand side in the fingerprint region, is the carbon to oxygen stretch. I wouldn't get too worried about that one. Okay, here's another carboxylic acid peak, and again you can see that big fat and ugly one in the middle, sorry, on the left, and then the strong one in the middle, which is your carbonyl peak. Yes, you've got a carbon-oxygen peak in that right-hand section, but there are a lot of peaks in there, and it's not always easy to distinguish which one is which, so don't get hung up about that stuff. Okay, now amines have, of course, nitrogen-hydrogen bonds. A primary amine has two nitrogen-hydrogen bonds. And so you see this tooth sort of shaped peak on the left-hand side with sort of two little teeth. I think of them as like little vampire teeth almost. And those relate to the two distinct nitrogen-hydrogen bonds. If you had a secondary amine, so you only had one nitrogen-hydrogen bond, then you would have just one pointy little peak there. It can be distinguished from your oxygen-hydrogen peak because it's not as strong and it's got more of a pointy end to it rather than a smooth parabola. And the other peak that you should note is that there's a peak about 1600 wave numbers, sort of moderately strong, and that one is the carbon-nitrogen peak. So you'll also see that in an amine. And here's another example of that. You've got your toothy peak on the left, and you've got your carbon-nitrogen peak as well. Okay, so that's the first thing you want to look for. The next thing is your carbonyl groups, which you will see generally between 17 and 1800 wave numbers. There are different ranges for different types of molecules that have carbonyl groups in them, but quite often the spectra that you'll see are not specific enough in terms of their scale to be able to identify these directly. However, you tend to see these very strong, not particularly broad peaks. With an aldehyde in particular, you see how you've got the carbon bonded to the hydrogen, the carbonyl carbon is bonded to a hydrogen, I should say, and that tends to lead to this secondary kind of shadow peak on the carbon-hydrogen bond stretch in the middle on the left-hand side. So that's the bit that's highlighted in green there for you. And that can be quite diagnostic for an aldehyde. Again, you see that there. A very strong carbonyl peak and then that diagnostic little shoulder peak on the carbon-hydrogen mess. Esters. Esters have both a carbon-oxygen double bond and a carbon-oxygen single bond, and so you get that very sharp peak at about 1750 wave numbers, which is your carbonyl peak, and you also get a relatively strong peak at about 1250, which is your carbon-oxygen peak. Reasonably diagnostic. So keep a lookout for that carbon-oxygen peak at about 1250. It can be quite useful. Ketones tend to have just the strong carbonyl peak and not much else. It can be misleading. That's why I tend to be wary of the fingerprint region, because this kind of looks like you've got a carbon-oxygen peak at 1250 as well, but in fact you don't have a carbon-oxygen single bond. So that's where you need to pull in information from your other spectra as well. So there's another ketone example. The ketones tend to be relatively straightforward. Now you've also got a peak at about 1650, which can represent the carbon-carbon double bond in an alkene. It's not usually that strong. It's not usually as weak as the spectra shows either, but it's nowhere near as strong as your carbonyl peak. Okay, there it is. It's quite a slender sort of a peak. There's really nothing particularly distinguishing about it. And if you've got a spectrum where you've got nothing in that sort of 3000 to 4000 range and nothing in the 1600 to 1800 range, and everything else looks really boring, chances are what you've got is an alkane, because let's face it, they are pretty boring. Okay, so I'm going to wrap up this video here, and I'll put in a second short video just about how we would go up matching spectra to compounds in a minute or 5. All right, I'll catch you soon.